Okay, plus, okay, I think we can start. Okay, can hear me, right? Everyone can. Okay. Okay, just anyone? Can you hear me? Response to make sure.
Yes.
Yes. Okay, good. Okay, so that day I introduced you the analog and digital. What is analog? A signal where the voltage value or the voltage value varies continuously with time. Digital as a series of high and low values. A series of high and low values, discrete values. Is this digital? Problem of analog, it amplify noise. So bad. Advantage of digital, it remove noise when regeneration happen. So digital is good. More advantage of digital, can encrypt the data. The circuit looks reliable, cheap and reliable. So we go for digital. Okay, so we're all going for digital. All the information is going for digitalization. Okay, so now the halfway we talk about this. So digital, actually what it does, there is a department ADC, convert the analog signal to digital. Okay, we go in depth about this today. Okay, so analog to digital converter, the analog voltage sampled at regular intervals. I told you that last class, the called sampling frequency. Okay, so sampling frequency, how frequent it take the sample. If the sampling frequency is very high, means the what do you call the width of the steps will be shorter. Okay, the steps should be a bit shorter. It's good. And voltage measures in sampling time converted into digital binary number. Okay, so the day I told you, you must know how to convert voltage to binary code for numbers. The maximum numbers they go, I think 16 volt, not more than that. Okay, so here something important at the third line, value given to the sample voltage, always the value of the nearest increment below the actual sample voltage. Below the actual sample voltage means what? An analog signal sampled at, they took the sample from the analog signal, is found to be 14.3, but when recorded, it will record it as 14. Okay, it will record it as 14. Why? Because the digital, the 4-bit, this is called 4-bit, 4-bit digital don't have any code for 14.3. You see the maximum voltage is how much? 16. So every 1 volt got code. 0 volt code is what? 0, 0, 0, 0. 1 volt, what is the code? 0, 0, 0, 1. So up to 16 volt, the code is 1, 1, 1, 1. 2 volt is what? 0 0.010. Continuous. So 4-bit only capable of 16 energy levels, only 16 energy levels. So this 16 volt, every 1 volt given a code. But unfortunately, when you take the sample, it was 14.3. So this 4-bit can't afford to give a code. It's good to have a code for 14.3, but it don't have. It only have a code for 14 and 15. So what the analog to digital converter do? He code it as 14. He put it lower. Always round down, go down. So if you have 3.8 sample, you're going to code it as 3. Okay. So this is the poor photocopying, like I say. You see, analog gives 14.3. When you sing a song with a different pitch and sound and everything, the pitch rises to 14.3 volt. But when the digital going to record it as 14, when this digital signal transmit again in a CD and you listen it from song from that CD, the 14.3 live band pitch, now you only from the CD you listen like a 14 volt pitch. The pitch won't be that good. The quality of sound will be what you call compromised. Because of what? Only 4-bit recording. You don't have code for 14.3. So remember, anything more than 14, not exactly fall at 14.12. Put it in 12.8. For example, you're going to drop to 12. The code. So like 12 volt means 1100. So code it as at 1100. Okay. So now that code, as I told you, will be modulated with the radio wave. Send it to your friend. When friend receiving into his phone, there is another department called. I go back. Another department called. Where is it? Digital to analog converter. Digital to analog converter. Now the digital signal will be retrieved from the radio wave, like AM, FM, right? FM, the frequency going to change only two type high frequency, low frequency, high frequency, low frequency. High frequency may be quoted as for 1 for digital, and low frequency might quoted as 0. That information retrieved from the radio wave, and this digital to analog converter do that. Then that digital signal will be converted to a trace back to a new wave. Trace back to a new wave. Okay, so you go back to that diagram. You see, here you see this is the original analog. This is the sampling done. This is the binary code sent to your friend. But in your friend's phone or TV, what do you call laptop, you're going to trace back this graph. See, it took sample 8, so you flatten it for 125. Flatten. Then at 125 seconds, he got a new sample 12, so you trace it out. So you flatten the curve. So what happened? This is the roughly looks like the original pattern, but can see it's like quite not that accurate because 4-bit not that good. So here, when someone singing a song, whatever song with a very different pitch variation in a short period of time, here it's not that good the variation. It's like the pitch like changing immediately. So this is digitalization. Why we do that? Because analog couldn't transfer without amplifying the noise. If any engineers or scientists found a technique that analog noise can be removed, I think it's not anymore digital world. It's going to be analog world. Remember, but currently digital is like can remove the noise. That's why we're using it. Okay, now the thing is, now the technology what trying to do is the tracing, the one you got here, they want to make it exactly or almost same as analog. Okay, how they can do that? They say by doing these two ways, you can do that. First, they say use more bits. Use more bits. Don't use for, maybe you can use 5-bit. Okay. If you use 4-bit, 4-bit is 1000. 4-bit means what is the total energy level you have? How do we find? This is times with this is converting binary to what do you call? Okay, sorry. Just for a while, I need to go to the open up the whiteboard. Okay. See, if you have 8, how do you convert to binary? So how do you convert to binary? So you divide, right? You divide 8, you put here 2, so 3 times 2, so balance 0. So 1 times 2, balance 1, balance 1. Then divide by 2, sorry, 0, balance 1. Okay. So the final answer until you get 4 numbers. So 8 is, I made a mistake. Sorry, what I'm doing is 4 times 2. 8, 2. 4 times 2 is 8, so balance is 0. So 2 times 2 is 4, balance is 0. Here by 2 again, 1 times 2, 2, so balance is 0. Now we stop here once you got 1. So the 8 is actually 1000. Sometimes they give a binary code to get the number. How do you get the numbers again? So first number you times it 2 power of 0. Second number you times it 2 power of 1. Third number 2 power of 2. fourth one is 2 power of 3. So add them all. So here 2 power of 3 plus they all are zeros. So all zeros. So finally get 8. This is conversion from binary to decimal. Okay. So 4 bits, 4 bits, because it has a 4 digit, 1, 2, 3, 4. The number of energy level you can have is 0, 0, 0, 0, 2, 1, 1, 1, 1. How much you have? You will have 16. You have 16 energy levels. How to get 16? Times now. This is 2 power of 0, this 2 power of 1, this 2 power of 2, 2 power of 3. So this is like 8 plus, yeah, so this is 8 plus this is what? 4 plus this is what? 2 plus this is 1, 1. So how much you get? You get 15. You get 15 different energy levels, excluding the 0, 0, 0, 0. You plus the 0, 0, 0, 0, you got 16. You got 16 energy levels. Okay. But let's say you use 5 bit. You intend to use 5 bit. 5 bit means you're going to use 5 digit. 5 digit. So how many energy levels you can have? So it's going to be 2 power of 5, 2 power of 4, 2 power of 3, 2 power of 2, 2 power of 0. Add them all. 2 power of 5 is how much? 32. So 32 plus this 4. This 4. That's now we. Sorry.
So it's 2 power of 4, 2 power of 3, 2 power
Oh
of
yeah. 1,
2 power of
2, 3, 4. Yeah. 2 power of 4. 2 power of 4 how much? 16. So 16 plus with 2 power of 3 to 2 power of 0. Just now we got how much? 15. So plus 15, how much you got? 31. 31 excluding the 0, 0, 0, 0 at this 1. So you'll have 32 energy levels. You will have 32 energy levels. That means if you have a voltage value, a signal with maximum of 16 volt, if you use 5 bit, you can have 32 levels. You can have 32 levels. Every how many volt you can keep a code? 16 divided by 32, how much? 0.5 volt. Every 0.5 volt you can have a code. Okay, that means you take a sample and the sample you got 15.5 volt. 15.5 volt your sample. 15.5 volt can have a code. You will have a code for 15.5 if you use 5 bit. But if you use 4 bit, 15.5 won't have code. So 4 bit will do what? The 15.5 is registered as how much? Registered as 15 volt. Because 15 volt got code. So use a 15 volt code. So this is bad. So how do you improve to be more quality, what do you call, transforming from analog to digital? Increase the number of bits, rise the bits. Okay, rise the bits. Your CD player, your CD player currently how many bits? I think now 16 bits. If I'm not mistaken, 16 bits. If I'm not mistaken, that means what? 16 bits. Imagine, that means they use 16 digits. 16 digits. 16 digits for coding. That means the first number is 2 power of 15. I think, or the number of energy level is so huge, million. I think maybe 15.51 also they might have a code. Understand? Your computer now is how much? How many bits? Your computer? Your computer now how many bits? Last time I think 32 bits. Now you have 64 bits. Your computer. I think now it's 64 bits. Remember the code, the digit they use 64 digits. So accurate, so accurate. Until the analog signal and digital look like it's the best photocopying the digit analog signals. So that's why we are go for digitalization. The technology is so improved so that it can merely can show the same analog signals, with not much of a difference. Okay. So go back to the slide. Yes. How to improve? Using more bits. Using more bits, what happened to the what do you call the steps? The height of the steps can be reduced. The height can be reduced. The height will be reduced. Increase the bits, the height of the steps is reduced. So more I could. Another one way of improving the digital signal is sampling frequency. Yes, take more samples. Instead, you see this graph, they put 8, 12, they can sample it at 125. You sample another one live. Maybe you can sample another one in between here, 70, what? 60, sorry, 62.5 seconds. You can get one sample here. So instead of one flat, you see, instead of one flat here, if you have a sample here, means the steps can become two, like this, like these two. This is more accurate. Okay, more accurate. Or if you take more samples, if you take more samples, let's say you take 5 samples in 125, I think this one steps, you can have, this one step can have like this step, one single one, you can have 5, 1, 2, 3, 4, 5. Like this is more accurate, portraying the analog shape. So how do you make more accurate? The width and the height of the step to be reduced. The height can be reduced by having more bits. The width can be reduced by having greater sampling frequency. Okay, this is quite very high nowadays. Now technology is very high until that digital is very accurate. Okay. Any question from this slide? Okay, let me continue. Okay, so bits and voltage levels. This is 4-bit system, this is 8-bit system. 4-bit 0001, 8-bit 8 digits. So you see the description here. 4 bits, the maximum energy level it has is 16. Okay, 8-bit, the energy level is 256. Okay, 256 voltage levels. So 256. Now you see this 8-bit, as I told you, CDs 16-bit, 2 power of 16. Very small energy levels. Small voltage rise also you can give a code. Okay. So yeah. So we're done with bits lah. More bigger the bit, more accurate the digital information which taking from the analog. But now, what sampling frequency do you do? What sampling frequency do you do? Okay, the choice of sampling frequency also determines the amount of information that can be transmitted. The greater the sampling frequency, more faithful is the reproduction of the original signal. The width of the the steps is smaller. About 100 years ago, someone recovered that the analog signal F, then the sampling frequency must be more than about 2F. Then it's good. You get the sample. So the sampling frequency used is 2F of the maximum frequency in the signal. What does this mean? Okay, let me show you some. Have you again go to the whiteboard to explain this. Okay. So let's say you have an analog signal. You have an analog signal like this, and getting like this and like this. Okay, so this one analog signal. Okay. So you have this analog signal. You want to digitalize it. Okay. How frequent you must take the sample? How frequent you must take the sample so that this pattern can be retained here? Okay. The frequency, the sampling frequency, the sampling frequency you must choose. Sorry, the sampling frequency you must choose is at least 2 times of the maximum frequency of the signal. The maximum frequency of the signal. So what do you do? The frequency in this in this signal is changing. You see period changing here, quite a long period, here short period. Okay, if so frequency is changing. Where the frequency, which region the frequency is maximum? Frequency maximum is here. Here the frequency is maximum because the period is short. Okay, so what frequency to be used is you need to they must take this sample. They can take more samples like they want. I think it's very critical for them to take this sample, and this sample. Okay, the 1, 2, 3, the 2, sample 2 must be collected. Okay, let's say 1 to 3 is separated by, let's say, 2 microsecond. Okay, and the 1 and 2 separated by 1 microsecond. 1 microsecond. Okay, 1 microsecond. This is 2 microsecond. Let's say the what do you call the analog to digital converter, analog digital sample as a sampling frequency. You use a sampling frequency of such as the period is 2 microsecond. Then what will happen to the signal? You take the sample, then can it collect the number 2 sample? You can't collect the number 2 sample. What will happen? It only collects sample after 2 seconds. So you take the sample, then immediately going to take the sample 3. You missed out the 2, you know. Missed out the 2 because sampling frequency is with a period of 2 microsecond is used. Okay. So what happened in the final tracing? They will get the stairs, they will get the shape like this, going down, going up, come down. But when it comes to this 1 and 3, you're going to trace as a flat and go down. You can't show that the graph going down and coming out. It won't show this because sampling is only on top. So you're going to flat here. Okay. So what they must do, the sampling frequency they must use with a period of how much? Period of 1 microsecond. Use 1 microsecond. If they use 1 microsecond, they can take the sample of 1. They will choose the sample of 2 because 1 microsecond they have to take sample. So they will take sample here, and sample here. So finally the graph will be at this portion will be up, then will go down and go up. So it will show the critical stages. Critical stages. Okay. So in exam, what you do? You look at the crest and the trough. Crest and trough. Check the duration where the crest and trough is quite close. The shortest time. Okay. Take the shortest time. Okay. For example, you see the crest here and the trough here is let's say 1.5 microsecond. Go and check in your what do you call in your signal. This crest and this trough, let's say it's the shortest, let's say it's 1 microsecond. And you take this crest and this crest, the third one, and it's 0.5 microsecond, let's say. So the sampling frequency you must choose. Sampling frequency you must choose. Okay, the sampling frequency you must choose is 1 over the period. The period must be the shortest period. How much is the shortest period? Yeah? So you must use the period of 0.5 microsecond, at least as the sampling frequency. Okay, at least the sampling. So take this time from the crest to trough as take it as the time duration period. Not crest to crest. Crest to trough only take the time. Okay, and that time 1 over that time is your sampling frequency. Okay, yeah, sampling frequency. This sampling frequency is twice of the maximum frequency. Maximum frequency. So yeah, so this is how you do. So any signal they have, they're going to check. Okay, the closest crest to trough, the shortest time. They take this time. They do 1 over t for that time. Okay, 1 over t for that time. Whatever frequency they got, let's say the frequency they got, let's say 20,000 hertz. They will do sampling slightly more than that, slightly more faithful. Maybe they go for 21,000 hertz. Okay, good. More bigger frequencies definitely better, but must be at least 2 times of the maximum frequency. Okay, maximum frequency actually we take the crest to crest. Okay, we take half as 2 times. So that's why we take half of the period actually, 2 times of the maximum frequency. Okay, so in exam, remember in exam, if they ask suggest a maximum frequency and they show what do you call, show signal. You search for crest and trough, the shortest time interval between the crest and trough, and that time you use frequency is 1 over that time, and whatever value you get, you put it more than this slightly. So the crest and the trough recoverable when they trace the digital shape. Any question, guys, from here? Very technical. So that's what here. In order to recover the analog signal of frequency f, then the sampling frequency must be at least 2f. Okay, at least 2f. So you see here, for good quality reproduction of music, the higher audible frequency is 20 kilohertz. We can listen up to 20 kilohertz. The sampling frequency they use is 44.1 kilohertz. You know, your CD all the digital digitalized at a sampling of 44.41, at least more than 2 times is used. Okay. So you know, your phone signal also digitalized. Human can sense up to 20 kilohertz, but human voice can give up to 1200 hertz. But I think from the Google, they stated like 3000 plus hertz. I think 3100 hertz of frequency can be produced by an opera singer, maybe. So this is the maximum frequency a human can make, 1200. But ordinary people, normally they can go for 1200 hertz when they talk to someone in phone, not like singing, but just speaking, 1200 hertz. So the maximum frequency of the sound could be 1200 hertz. The sampling frequency was made 1200 times 2. How much? 2.4, 2400. They use sampling of how much? The highest frequency transmitter is restricted to 3.4 kilohertz. Sampling frequency was 8 kilohertz. As I said, opera singer is like 3100. So 2 times of this, 6200, they put 8 kilohertz. Comfortably very high frequency they use. 8 kilohertz use for your phone sounds. But rule is, you want to use sampling frequency, must be at least 2 times of the maximum frequency. At least 2 times of the maximum frequency in the signal. That's your sampling frequency. Okay. Any questions? Can I have? Okay. So now we're done with digital. Okay, let's do some question to understand the concept. Okay, look at this question. Everyone, give a try. An analog signal is sampled at a frequency 5 kilohertz. Sampling frequency is 5 kilohertz. Each sample is converted into 4-bit number. 4-bit is used. 16 energy levels and transmitted as a digital signal. Okay, show part of the digital signal. The digital signal transmitted finally also 10.1 shows the part of the signal. Show the signal. Okay, this is the binary code given. It's a 4-bit. Sampling frequency use how much? 55 kilohertz. Okay, now what they want? The digital signal is transmitted and finally converted into analog signal. In the axis of 10.2, sketch a graph variation with time t of this final analog signal. Yeah. So they're asking how this digital when this digital signal converted to analog, how the graph going to looks like. Can you trace this analog signal recovered from digital? Okay, first, what you need to know is, you need to know what is the first number belongs to. How many volt is this? 0010. How many volt is this? 1 volt, one code. 1 volt is 0001. This 0010, how many code? What voltage? Anyone? So 0010, first times is 2 power of 0, second one is 2 power of 1, third is 2 power of 2, 2 power of 3. So what do you get? This all are 0, 0. 2 power of 1 is 1, so it's plus 2. 2 power of 0 is, this also 0, right? 0, so it's 2. 0010 is actually 2 volt. It's 2 volt. So what I do? You take the 2 volt, at 2 volt, you have to draw a flat line But what is your sampling frequency? Sampling frequency was 5 kilohertz. So frequency 5 kilohertz means what is your period? Find the period. Period is 1 over 5 kilohertz, 5000 hertz. So what is the answer you get? I think you get 0.2 milliseconds, if I'm not mistaken. So the 2 volt 0.001, 0010 is 2 volt. It's going to be flattened up to 0.2 milliseconds because sampling frequency period is 0.2 milliseconds. Then after that, next, how much? How many volt is this? 0100, 0101, sorry. 0101, how many volt? Anyone? 0101, how many volt? It will be 5 volt. So the graph will go up to 5, so flatten. So this is how the tracing will be flattened for another 0.2. Then next is 1010. Look at answer is 10. So it'll go up to 10, flatten. Then go up to 15, flatten. Then go up to 4. Go to 4 again, sorry. Go to 4, flatten. This is how the analog break out from digital looks like. Okay. Any questions? So find the period of the from the sampling frequency. The period tells the flat line how long. Okay. So this is the first sketch lah, 5 kilohertz, and the digital code you must know how to convert to volt. Okay. B, suggest 2 ways in which the reproduction of the original analog signal could be improved. There are only 2 ways lah. What is that? Sample more frequently, greater number of bits. Sample more frequently, the width of the steps reduced. A greater number of bits, the height gets smaller. So more quality, better reproduction. Any questions from here? Okay. Yes, that's about digitalization. Okay. So you have to know this. Okay. So let me go to the some example. That's it. We do some questions first. Bear with me. Okay, so you have questions from telecommunication. Maybe one question. Okay. So this is your telecommunication. Okay, we done this just now. Okay, this is one. We go for digitalization. This is AM. We already done this. This is AM. I go for digital. Check. Okay. Okay. Yeah. Number 9, paper 41. Question 12. So, what is the answer? How do you answer the part A? So, what is the advantage of transmitting information in digital rather than analog? So, what's the answer? You can say digital. The noise can be removed while regeneration, whereas analog, the noise will be amplified. Okay, so that's one main advantage of digitalization. Another one advantage of digital is what? The circuit is reliable and cheap. Okay, you can do that, or you can say can add more information in the digital information, can encrypt the data. That's all advantages. Okay, next, convert the decimal number of 13 to 4-bit digital number. Okay, come on, give me the number. 1 minute for you. Give a try. 13 convert to digital. Give me the number, 4-bit. So anyone? So how do you do? So put the 13 here.
1101.
1101. All of you got this. Okay, good. Next, you must divide up till you get 1. Until you get 1. So 1, then another 3 digit at the sideline. You must use it as your binary code. Okay, next. 0101, this is decimal, what do you call decimal number? 5, right? Hope you get 5. So this is 2 power of 2. So 2 power of 2 and 2 power of 0 plus. So it's 5. 5, good. Yeah. Okay. So this is AM. Let's keep this. Digitalization. It's all our past years. I already posted this. Give a try. Okay. 12A. What's your answer? Explain what is meant by analog signal. So analog signal is a type of signal where the voltage or the power varies continuously with time. Okay, varies continuously with time. What is digital signal? It's a type of signal which has a series of high and low voltage values. Okay, it has a series of high and voltage values. It's digital signal. Okay, 1010. State two advantage of transmission of data to digital, or this I don't know how many times they repeat this question. As I said, telecommunication might be quite new for you, but the questions are rigid. They can't ask a lot. Okay, I post here I think about 10 years or 8 years of past year questions. You go through that, I think roughly you get to know what they're going to ask for. The question is rigid. Okay, so frequency modulation we done that day. We skip this first. Corporate. Yeah. Okay, so yeah, so that's about it lah, and digital. Okay, so now we go to the, we need to finish this syllabus, so we have another 1 slide to go. Let me go through the first half. Okay, so next is the part 3. Okay, so this is the last slide which end the syllabus. Okay, I can't finish today, of course. I need to have 1 extra class tomorrow. Do you have any? I plan to have on 10:30 tomorrow, 10:30 to 12 to finish off the syllabus. Do you have any classes, extra class tomorrow? If any concern, you can put it in the WhatsApp. I send the details now. Okay, so the last thing we're going to talk about is attenuation. I won't talk about attenuation now. I straight go to the next part first. Attenuation, I put it as the last. Next, it's about satellite communication. Okay, this is a fact to remember. Let me go through this first. Okay. Okay, so satellite. Okay, we learn under gravitation about satellite. Okay, what is satellite? Why we need satellite? Why communication satellite is required? Communication satellite requires is a long distance communication using a radio wave. Yeah, long distance communication with the radio wave has a major disadvantages. The landline, the skywave has a variable quality of signal because the ionospheric is unreliable because its density depends to the weather. That's why skywave is not reliable. Although skywave is global, can transfer the information worldwide, but we can't depend to the ionosphere. The densities depend to the weather. The surface wave are also unreliable because poor reception in hilly areas. Hilly areas surface waves are bad, cannot diffract. Okay, and another one thing is the wave bands are in the medium wave and short wave already crowded. The lower frequency are already crowded in 1950s, 1960s. We only have the low frequencies. It's already used up by all the companies, all the radio transmitting companies. So we need to have a new wave bands. That means we have to move on to a high frequency. So available bandwidths are too narrow. So to carry the required amount of information. So satellite communication enables wave bands to be made available at high frequencies, higher frequencies, thus giving the rise much greater data carrying capacity. Yeah. Because high frequency are not occupied by anyone. Because you want to have high frequency, you send the high frequency to the sky means the high frequency has a very high penetrating power. It penetrate, pierce the the atmosphere, go to outer space. So the ionosphere can't reflect it. So high frequency need a reflector. Who's the reflector? Man-made satellite. You have a satellite out of the outer space. So let the high frequency signal go and hit the satellite, and the satellite amplify the signal and reflected it. That's why satellite communication was needed. Okay, why satellite needed? To have because of these three reasons. Sky wave unreliable, surface wave bad in hilly places, lower waveband already crowded. So satellite communication is needed. Okay, now satellite send a signal from the ground station. A signal was sent to the satellite. Satellite does do two jobs. It reflect as a reflector, act as a reflector. Another one, it amplify the signal. Okay, it amplify the signal. The signal which reach at the satellite is highly attenuated. Highly attenuated. That means it loses lots of power. So the satellite have to amplify the signal at the same time reflect the signal back to another part of the world. So a carrier wave of F up is sent from a transmitter, Earth satellite. The satellite receives the greatly attenuated signal. The signal is amplified and carrier frequency is changed to a lower frequency down. So going up with one frequency, come down will use another frequency. Okay, why they must change the frequency? There is one reason. The reason is the carrier waves then directed back to the receiver are the F up and F down are different, so that very low power signal received from the earth is not swamped, to prevent swamping. Why to prevent swamping? You see, if both frequencies same, at a satellite, the one going in is weak energy, very little energy. The one coming out is lots of energy. Because if the frequency same, resonance will happen. If resonance happen, all or most of the energy of the output signal will channel back into the input again. Like feedback in op-amp, the feedback will happen. The energy will transfer back to the input signal. So the output signal cannot reach the land. Why? Most of the energy has been absorbed by the input signal again. So you can't transmit the signal down because swamping happen. Why swamping happen? If the frequency is same, swamping will happen. Why frequency same, swamping happen? Because resonance happen at same frequency. So to avoid energy from the output signal to transmit absorbed by the input signal, we need to use a different frequency so that resonance never happen. So that's why use down frequency always smaller than the up frequency to prevent swamping. The high power signal that is transmitted back to the earth. Okay. Values of uplink and downlink frequency might be 6 gigahertz, 4 gigahertz respectively. Okay, one past year they asked, give a example of what up frequency, down frequency to be used. So far they use 3 types: 6.4, 14.11, 30.20. You have to memorize this frequency. Okay, 6.4, 14.11, 30.20. This is what frequency has been used in the satellite transmission. Okay. So when transmitting signal, use a satellite dish. Okay, when receiving also, satellite dish is used to receive back. You see the signal was hitting the satellite dish and parallel beam was produced. And ditching back also, the parallel beam hit the satellite dish and reflected to the receiver, and you get the signal. Okay. Okay. So that is about satellite. Geostationary satellite. Geostationary satellite orbits the Earth above the equator. It has a period of 24 hours and rotate from west to east. Okay, west to east from the Earth, from Earth rotation. West to east, 24 hours of period. Period of 24 hours. Move from west to east. Always stays in the same location above the Earth location, If the satellites in exam they'll ask, what is meant by, what is the picture of geostationary satellite? So you have to say this, or another one is three features. The geostationary satellite is always above equator. The orbit is always above equator. It has a period of 24 hours, and it moved from west to east. It moved to the direction of the Earth rotation. Okay. If the satellite is orbiting at the same direction as the direction of rotating the Earth, for observer on the Earth, the satellite will always appear to above the fixed position of the equator. Okay. So to connect the world, you need 3 satellites. Okay, you need 3 satellites. You put another one here, you have another one here, you have another one here with an angle of separation, the angle of separation of 120 degrees each. You can cover the entire world at the site. Okay, so any live telecast happens at maybe Malaysia is here, and let's say Olympic happens in Brazil, or let's say in Brazil. So this satellite will take the information and send it to this satellite and send it to you back. Okay, to the transmit to Malaysia. Okay, so 3 satellites required. Live telecast, just satellite is good because always sticks on the same location. Okay, so advantage of geostationary satellite, it always in a fixed position. You have a permanent link. Okay, you have a permanent link, and can maintain the community with any point of the Earth's surface. Yes, you go to the Bukit Jalil. There is a Astro main quarter. At the outside, they put a very huge satellite dish to transmit. This satellite dish, right? This satellite, the dish, you no need to turn around. It always fixed at one direction, always connected to the satellite on top of Malaysia. So it always in a fixed position. So permanently, you get a permanent link, always connected to the satellite. Okay, like this diagram you see, the dish is here, always facing the satellite. Okay, but there is some disadvantage of this geostationary satellite. The disadvantage is it cannot connect polar region. Okay, means what? You see this picture. If any live telecast goes on at the center close to equator, you can take the signal. But you see the Arctic and Antarctic is not connected because it only hit the side. This picture is better. You see, it only hit the side. It can't reach the Arctic, the North Pole, and also the South Pole here. So that's one disadvantage of geostationary. Disadvantages is communication in polar orbit is not possible. So another one big problem is the delay. Geostationary satellite has a huge delay because of what? It's very far away from the Earth. To get a period of 24 hours, it must put a radius of very far away. Okay, so therefore the signal by the time go and hit the satellite and reach you back, it takes very long time. You can see that in CNN news sometimes. You see in the CNN, the TV, the first one, maybe the person who are asking question from maybe from UK, another one answering from maybe from Japan or something. You can see when she asks the question, the other guy won't answer immediately. You need to wait for a few seconds, about 0.24 seconds before he answer the question. So there is a delay. Okay, the satellite from the UK go to the geostation above the UK, go to the another satellite which on top of Japan and sent to the Japan. So it takes time, delay. It's a great delay. Okay, so to overcome these two problems, what we do, what the scientists did, they introduced another satellite, another type of satellite. It's called polar satellite. It's called polar satellite. Okay, polar satellite is a satellite was launched from north to south. It moved north pole to south pole. It go vertically. What do you call geostationary satellite is a equator. What do you call orbit? Okay, very far away. But polar orbit satellite is north to south pole, and it's very close. It's very close from the surface of the Earth, just above the atmosphere. You know. Okay, polar orbit satellite have low orbits, very low orbits, pass over the poles. Okay, polar orbit satellite have a period of only 90 minutes. Only 90 minutes. That means it makes how many rounds? 16 rounds in a day. 24 divided by 1.2, 1.5. How much you get? I think 16 rounds. So polar orbit satellite makes 16 rounds in a day. Okay. And you see, and the polar orbit satellite go one round, the Earth rotating to this direction. So maybe the first time, let's say it passes Malaysia, after 1.5 hours, when it come back to the location, it might pass Indonesia because Earth is rotating. Yeah. By the time the satellite comes back, maybe the Earth rotation causes our Malaysia skip to the right. The Indonesia will be on top of that satellite. So 24 hours, it seems the satellite, the polar orbit satellite, can inspect the entire world. You can see the entire world in 24 hours. Okay, each day orbit about on the surface of the Earth. Okay, the orbit crosses the equator 23 degrees to the west of the previous orbit. So yeah, 23 degrees to the west. It goes to the west. Because we view from the top, it's 360 degrees, 16 rounds, 360 divided by 16 rounds, how much you get? You get around 23 degrees. So every round it comes back, the Earth already rotated 23 degrees from the axis. So yeah, each orbit crosses the equator 23 degrees to the west due to the Earth rotation. Okay, so this is called polar orbit satellite. Polar orbit satellite is made just to overcome these two disadvantages owned by the geostationary. Polar orbit satellite has these two overcome. Polar orbit satellite the advantage is it connected to the North Poles and it's very fast transmitting the signal. The delay is very small. But polar orbit satellite also not perfect one. It has a disadvantage. The disadvantage is continuous communication is not possible. Okay, continuous communication is not possible because you see the polar orbit satellite. Let's say there is an Olympic goes on in Brazil. The polar orbit satellite go to the Brazil on top. Maybe it stays there for 2 seconds. Maybe after 2 seconds you're going to leave the Brazil, and maybe you're going to reach the Brazil again after 1 day later. So by the time if it's a World Cup is there for, so you can't rely on one polar orbit satellite. So continuous communication is not possible. Okay, way to overcome, how to overcome this continuous communication to make it possible, you have 100 over or maybe 1,000, maybe 100 over orbitals, what do you call, polar orbit satellite rotating at that region every second. When one pass by, another satellite will be on top of the Brazil. Maybe every 25 degrees there will be one polar orbit satellite. This is the Earth. You have one polar orbit satellite here. You have another one polar orbit satellite here. So any polar orbit. And one skip, another one polar orbit satellite will be reaching the Brazil. And this all polar orbit satellite will be monitored by one station at the ground. So continuous transmission is possible. Okay. Ways to overcome, data stored, transmitted back to the Earth over the appropriate area. using a number of polar satellite orbits that incline another, so that at least one satellite always above the transmitter receiver. This aerial must be tracked satellite in their orbits. See. So your GPS uses polar orbit satellite. Your GPS using polar orbit satellite. We can't use geostationary. Why? There is a delay, 0.24 second. You know, if you use geostationary for your GPS, I think by the time you say turn left, you already passed the junction. Okay, so polar orbit is used for a GPS. Okay, so that's all about satellite. Okay, guys, any questions so far? So this is a fact to remember. So we're done with satellite already. So read through to understand about the satellite. Okay. Tomorrow, just I spend around 1 hour, maybe 10:30 to 11:30 to finish off the attenuation. Okay. Then we're done with the syllabus. Okay. Any question? No questions? Okay. I stop here. So see you tomorrow around 10:30. Any concern, you just put in the WhatsApp. Okay. Thanks.